Today we are going to, good morning students. Today we are going to look at another topic, that is energy and energy changes. That is the topic we are going to start today. But let's invite God into our midst. Dear Lord, we thank you this morning for bringing us together again. We are asking you to come and steer the affairs of this meeting. Speak through me to impart the knowledge of this topic to the student that I have before me. And in the end, when everything becomes very successful, your name shall be praised. In Jesus' name, amen. Energy is the ability to do work. Energy is so important, especially in our modern society. For us to be able to drive to our workplace, energy is required. For our industries to be able to produce goods, energy is required. Me being able to speak to you this morning, I'm using energy to talk to you. So energy is very, very important, especially in our modern society. There are two forms of energy, and that is, we have potential energy and kinetic energy. Potential energy is the energy that a body possesses by virtue of its position. So it's like work is not being done yet, but that object has the potential to do work. Example of potential energy include nuclear energy. That is the energy stored in the nucleus of atoms. Energy stored in the nucleus of atoms. We have chemical energy. That is energy stored in chemical bonds. Then we have stored mechanical energy. Here we are talking about energy that is created in stretch springs and rubber bands. Then we have kinetic energy. Kinetic energy is the energy that a body possesses by virtue of its motion or movement. So we can think of kinetic energy more as an action energy. Example of kinetic energy include thermal energy. Sound energy, electrical energy. We have so many of them, like radiant energy, thermal energy. We are talking about the internal energy of atoms, substances, and molecules. When we talk about sound energy, that is the energy produced from stretch or pressure on stretch of waves. Then when we talk about electrical energy, we are talking about energy that is produced as a result of movement of electrons. Radiant energy is the energy from the sun, the electromagnetic waves from the sun. That is the radiant energy. For the purpose of our topic, we will be focused more on chemical energy and thermal energy. As I've already defined, thermal energy is the energy that is the internal energy of a body. When thermal energy flows, we have heat energy. The heat energy cannot be measured, but we can measure temperature. Usually students confuse, or people confuse temperature with heat energy, even though these terms have been used interchangeably on many occasions, but they are not the same. Temperature is the measure of average kinetic energy of a body. So when heat energy, when the internal energy flows, then we will have temperature also increases. So as internal energy increases, temperature also increases. So we can say that what they have in common is that we can use temperature to determine heat energy. And that is what in this topic we will be doing. What we are going to discuss now, we are going to look at two main terminologies under this topic, that is systems and surroundings. What is a system? A system is a part of the universe that is under study. It is the part of the universe that is under study. And surroundings it is the rest of the universe outside the system. So diagrammatically, let's say we have this as our universe. And let's take the circle here as our system. So what we are interested in is the system here. We are concerned about whatever happened here. For example, if I take HCl and I add it to sodium hydroxide, we'll be expecting a reaction in this system. So the reaction that is taking place here is our concern. That is what we wish to study. That is what we wish to know. We are only concerned about what is happening in the system. So that is why we have defined system as what? That part of the universe that is under study. That is, we are interested in what is happening in, let's say, a beaker in which the acid and the base have been mixed together. We are interested in what will happen there. So that is the system. Outside this system, just like supposing we are doing this reaction in a laboratory room, the laboratory room becomes the surroundings. Become the surrounding. So we have a system and we have the surrounding. The system and the surrounding together gives us the universe. However, the system and the surrounding, they are separated by a boundary. The boundary, I mean the line here. The boundary here may be physical or imaginary. Physical in the sense that, let's say, if you have acid and a beaker, you have acid and a base in a beaker, the walls of the beaker becomes the boundary, which is separating the acid and the base from the rest of the laboratory room. So the boundary between, that area between the surrounding and the system is what we call the boundary. The boundary always separates the system from the surroundings. But there is an interaction between the system and the surroundings. The system and the surrounding can interact. By interaction, we mean they can exchange something like energy, heat energy, as we are talking about, or they can even exchange mass. For example, if in a beaker here, I have HCl and I add a powdered sample of zinc, there will be a reaction, that is the HCl will react with the zinc to give us zinc chloride and liberate hydrogen gas. Once the beaker is open, this hydrogen gas can escape from the beaker. And if this reaction also produces heat, there could be a transfer of the heat from the beaker to the surroundings. So there is always an interaction between the system and the surroundings. But the interaction between the systems and the surrounding may vary or may differ from one situation to another. And this will lead us to 3 types of systems. So we have system. And the system can be divided into open system, closed system, and isolated system. Now, what is an open system? It is a system that exchanges both matter and energy with its surroundings. Once again, an open system is a system that allows the transfer of matter and energy across its boundaries. Don't forget, we have already talked about boundaries. That is the boundary that separates the system from the surroundings. So a system that will allow an exchange of matter and energy across the boundary is said to be an open system. An example, so if we have an open beaker here, and in the beaker we have, let's say, HCl reacting with zinc. This reaction will produce gas. The gas can escape into the surroundings. The same way particles, air, dust, everything that's also in the surrounding can also come into the beaker. The same way heat generated from this reaction can also move into the surroundings. And the same way, if supposing the surrounding temperature is higher than the system, heat can also move from the surrounding into the system. So any system that allows exchange of matter and energy with the surrounding is described as an open system. Now let's look at closed system. For a closed system, we still have our reaction taking place here. We have our HCl and our zinc. But this time, the beaker is sealed. The open part of the beaker has been covered. So the gas that will be generated from this reaction cannot escape. So at the end of the reaction, mass of the system will remain constant. But energy, because we've not done anything to prevent the transfer of energy. So energy, in this case the heat energy, can move out of the system the same way heat energy from the surrounding can also go into the system. So for this system, we are only preventing the transfer of matter, but we are still allowing exchange of energy, which is heat. So a system that allows an exchange of energy across its boundary, but does not allow exchange of mass or matter across its boundary, is described as a closed system. Let's look at isolated system. For the isolated system, the system, we have covered it to prevent transfer of mass. And we have also used insulating materials to also insulate the beaker. So we can have the reaction taking place. The gas that will be generated, which is the mass now, cannot escape because we have covered the beaker. And we have also we have provided an insulating materials around the beaker. So heat transfer cannot also be exchanged across the system. So because the system cannot allow exchange of matter and mass with the surroundings, this system is referred to as an isolated system. So it's more to say that the isolated system cannot be influenced by its surroundings. But let me quickly add this, that we don't have a perfect isolated system. Most of the time, the common example we give on an isolated system is the vacuum flask or the Thermox flask. It's able to work up to some extent. When you keep hot substance in it, it can keep it hot for a certain amount of time. But if you have tried that, you see that the longer you keep it, the substance will finally become cold. This tells you that we don't have a perfect isolated system. So we have three types of system. An open system, which we have discussed, is the one that allows exchange of matter and energy across its boundaries. Then we have a closed system. Closed system is a system which only allows a transfer of energy across its boundary but does not allow exchange of a mass or matter. Whilst isolated system is the one that allows exchange, the one which does not allow exchange of both matter and energy across its boundaries. Chemists, we are more interested in the system because that is where our reaction takes place. We are concerned about the energy involved in the reaction. So our focus is mostly on the system. Now, let's say we have a cat. Let's just use this to stand for a cat. So the cat takes in food, and during the metabolism of the food, the cat will produce energy. The energy that the cat produces may be transferred into the surroundings. So in this case, the cat is the system, and we have our surroundings. So in this case, we have the system losing heat to the surroundings. We have the system losing heat to the surroundings. Let's look at another scenario where we have an ice cube. And if the ice cube is melting, what is happening is that heat is being taken from the surroundings into the system. So here the ice is the system and heat is, so here what are we having here? We are having the surrounding losing heat to the system. Whilst in the first scenario we have the system losing heat to the surroundings. This will lead us to two types of reactions. A reaction the reaction here I'm referring to the system. The reaction in which heat is taken from the system into the surrounding. In other words, a reaction which produces heat into the surrounding or which releases heat into the surrounding, and also a reaction which absorbs heat from the surroundings. This will lead us to two types of reactions which I've mentioned. So we have what we call exothermic reaction and endothermic reaction. So we have exothermic reaction and endothermic reaction. So what is an exothermic reaction? An exothermic reaction is a reaction that releases heat from the system into the surroundings. So when exothermic reaction occurs, the system loses heat. So the heat content of the system goes down, whilst the surrounding temperature increases. So exothermic reaction is a reaction that releases heat from the system to the surroundings. And examples of exothermic reaction include combustion reaction. Combustion reaction. That is burning. All combustion reactions are exothermic reactions. These reactions releases heat to the surroundings. For example, you go to the kitchen, you turn on the gas, you light the matches, and you begin to burn the gas. That's combustion reaction. This reaction produces heat, and it is the heat that you use to cook. So you can see that when you burn the gas, it's not only the heat that you are producing, but you are not interested in the other products that will come from the reaction. For example, if you burn methane, you produce carbon dioxide, water, and heat. So carbon dioxide is being produced, water is being produced, but in the kitchen, you are not interested in these products. What you are interested in is the heat energy, because that is what is important to you. That is what interests you. And that is what you need to use to cook your meal. So exothermic reaction releases heat from the system into the surrounding. An example is combustion reaction. Another example is neutralization reaction. That is a reaction between acid and a base. Reaction between acid and a base releases heat, even though the heat that they release is not as much as the one we will have in combustion reaction. So mostly you realize that in neutralization reaction we are more interested in the other products than the heat that is being released, because the heat is not very significant, but it's a reaction that produces heat. We can also talk about dissolving alkalis, that is bases that are soluble in water. For example, if you have sodium hydroxide right now and you put it in water, as the sodium hydroxide dissolves in the water to form sodium hydroxide solution, when you touch the beaker, you feel that the beaker is hot. This tells you that the dissolution of the sodium hydroxide, which is an alkali, is an exothermic reaction. The same also goes for acids. For example, if you take H2SO4 and you dissolve it in water, there will be a release of heat. So that's also another exothermic reaction. Then we also have oxidation. Oxidation of metals. Oxidation of metals also releases heat from the system to the surroundings. Now let's look at endothermic reaction. Endothermic reaction. This is a reaction which absorbs heat from the surroundings into the system. This is a reaction that absorbs heat from the surrounding into the system. Such reaction will lead to an increase in the internal energy of the system and decrease the temperature of the surroundings. Example of endothermic reaction, we have thermal decomposition. For example, if you have calcium carbonate and you apply heat, it breaks down to give you calcium oxide and carbon dioxide. This is a thermal decomposition. Heat must be absorbed. Energy must be absorbed to be able to cause the dissociation or the decomposition of the calcium carbonate. We also have dissolving certain ionic salts, such as ammonium chloride, potassium nitrate, etc. When these salts are dissolved in water, the dissociation reaction of the salt is endothermic. Heat is absorbed from the surroundings into the system. Therefore, the temperature of the surroundings drop as the internal energy of the system increases. I've already told you that as chemists, we are more interested in the energy that is involved in these reactions. So now we know that for exothermic reaction, it involves energy. That is, energy is released from the reaction, which is the system, into the surroundings. And for endothermic reaction, energy is absorbed from the surrounding into the system. So we are interested in the energy changes that takes place in this reaction. Now, let's use this analogy to look at the sign convention of the energies involved. Now, let's say you have a bank account with this amount of money in it, and you are withdrawing the money. You keep on withdrawing the money. So you are withdrawing the money. So this is more like a system losing energy. As you keep on withdrawing the money, with time, what will happen? Your money left in the bank will become small than initial. So this is what happened during exothermic reaction. At the end of the reaction, the heat content of the system becomes small because it has been losing what? Heat to the surroundings. So this is just like you having enough money in your bank account and you keep on withdrawing the money. So with time, the money left in your bank account becomes very small. And of course, this is a negative thing. It's a negative thing because you are losing money. So it's negative. So for that matter, exothermic reactions, the energy involved have a negative sign attached to it as a convention. We can also use the same analogy to explain endothermic. So let's assume that you have a bank account with small amount of money. Then you keep on adding money to that bank account. So with time, you are going to have more money in your bank account. This is what happens in endothermic reaction. The reaction produces heat. The reaction absorbs heat. So with time, the internal energy, the heat content of the system will increase. And this is a good thing, because if you have small money and you keep on adding more money to it, it's a positive thing. You are increasing in your money side, so this becomes positive. So for endothermic reaction, because the system is gaining heat energy, the conventional sign for the delta H or the heat change for endothermic reaction is positive. So whenever we write a reaction and we want to indicate whether it is exothermic reaction or endothermic reaction, the energy involved in that reaction is attached to it, and a sign, either positive or negative, is used to indicate whether the reaction is exothermic or endothermic. So as I've explained to you, for exothermic, the system loses heat. So the heat content of the system becomes small. And as we have said, that is a negative thing. It's like you have money in your bank account and with time you are losing the money. And that is a negative thing. Your money becomes smaller. So for exothermic reaction, the energy change that will be attached to such reaction will have a negative sign. Whereas for endothermic reaction, the energy change that will be attached to the reaction will have a positive sign. And whenever we write a chemical equation, for example, let's say hydrogen gas plus oxygen gas giving me water, and we say that delta H, that is energy change or the heat content of this reaction, is let's say negative 241 kilojoules per mole. This, we are talking about a chemical equation which is also taking into consideration the energy involved in that reaction. Such a chemical equation which takes into consideration the energy involved in that reaction is called thermochemical equation. So a thermochemical equation is a chemical equation which accounts for the energy involved in that reaction. All the time, we know that some reaction, we can have a forward reaction and we can have a reverse reaction. Whenever a thermochemical equation is written and the delta H figure is attached to it, the delta H figure is for the forward reaction. So for example, if I have water in a solid form, that is ice, and is converted to water in a liquid form, for this to happen, energy has to be absorbed. So this transition or this process will have a negative delta H value. The heat will be absorbed in order for the ice to melt into liquid. So delta is, so I've written this thermochemical equation and it's showing in this direction that when the solid water, which is the ice, change into liquid, energy is absorbed. Now, if we are to have a reverse of this reaction, So this is a thermochemical equation where we have solid ice absorbing water, absorbing heat to melt into liquid. This reaction is absorbing heat, so the delta H will rather be positive, not negative. This reaction is absorbing heat. Now, if we want to have the reverse of this reaction, where we have the liquid water changing back into ice, how can this happen? We can do this by placing the water in a fridge or a freezer, if you want. So that the water will keep on losing heat. So now we rather have water as the system losing heat to the surroundings, and therefore for the liquid water to change into ice, energy will have to be released. Therefore, delta H for this reaction will be negative. So you see that the first reaction, when you compare the first reaction to the second reaction, you see that the second is a reverse of the first one. So whenever we write a thermochemical equation, the delta H figure attached to it is for the forward reaction. We will end here today, and in our next lesson, we will continue from where we have ended today. Thank you very much.